This is a video for learning the distribution for inferring about slope and a hypothesis test for slope. What we are starting with is the distribution for slope. What we're trying to do is infer what the population slope will be based off of the sample slope. And I'm going to run through this document of notes here. I will also post this page of notes. And we are going to start with the center. Center of the distribution will be the point estimate as always, and that is the sample slope, denoted B sub 1. And if you want to take a look at example 13.4 and 633, read through that would be a good idea. I'm going to do a quick synopsis of it here as well. What we're trying to do in this chapter is track Q to Q, X, Y. And we have data points scattered, whatever that might look like. And we're going to take those data points, and these are from a sample. And we're going to make a regression line based off that sample. Now that doesn't mean that's exactly what the population does. Maybe the population has some more points down here or some more points up here. So that means the slope could be a little lower. This is the slope. The line has a slope that matches our sample. But the true population slope could be a little flatter. Could be as low as this. Or the true population slope could be as high as this. Now, that's a little bit of an extreme difference. I'm just using it for clarity. And we can see whatever this slope is could be as high as this, could be as low as this, and we're going to do a confidence interval for that at one point. But right now, we're just testing to see, here's my sample slope. Within a certain margin of error, what's my population slope? Let's infer whether the population slope is something or not. Typically what we're going to do is we're going to infer is it 0. But understand, it could be a wide range. And in fact, the more spread out the points are, the bigger that difference might be between our sample and what the actual population slope is. So this line is the center. It's my best guess, the point estimate. The slope of this sample line is my best guess, point estimate. Now the spread, how spread out could that be? Comes from a formula, the standard error, SE sub B sub 1. This is not typical residual size. It uses it, but this is not typical residual size. SE sub B sub 1 is the slope standard error. It takes the typical residual size S and divides by this formula, the square root of the summation of each x minus the mean of x squared. This isn't too terribly difficult to calculate, but we are not required to in this class. So SE will be given to you or will be calculated using software. Okay. The shape of a sample slope, it is a T distribution, and it will be normal if the sample size is large enough. Few relationship items. If the typical residual size S is large, then the spread of the slope will be large. So if I have points really spread out, points up here, down here, that typical residual size is going to be much bigger, which means my population slope could vary much more because those points are more spread out. A small spread is better, obviously, so that we can be more accurate in our inference. And as always, the larger the sample size, the more accurate we're going to be. That's just a quick synopsis on the distribution for slope with a T distribution. Let's jump into the hypothesis test. And again, I will have this posted, so if you want to take a look at it, maybe even print it off and follow along as we go through this. Hypothesis test. When we write a hypothesis, there are two ways to write it. We're going to do parameters and variables, and we're going to do them at the same time. Null, H sub O. Beta sub 1, the population slope, is 0. In terms of parameters, my slope, the unknown population slope, is 0. In terms of variables, there is no relationship between whatever the two variables are. Now think about the connection between these. If the slope is 0, that means I have a flat line, like this pen right now. It's completely flat. There's no slope. And if there's no slope, that means y is not changing as x increases. And if y is not changing, that means x is not affecting y. So it's a flat line. There's no slope. So if there is no slope, there is no relationship. Now, there's 3 ways to do the alternative, and each one means something different. If we do not equals to, that means there is a relationship. If the slope is not 0, y is changing as x increases, which means x is affecting y in some way. But most of the time, we're not going to use not equals to. We're going to be more specific here, and we're going to take a look at alternatives of greater than or less than. If my slope is greater than 0, then I can say specifically that there is a positive relationship, which means y is increasing as x increases. And if it's less than, there is specifically a negative relationship. Once I've written my hypotheses, we're going to check our bias, which you learned yesterday, checking the 4 conditions from yesterday using those graphs, the scatter plot, the histogram, the box plot. Then I'm ready for my summary. The test statistic, T, is B sub 1, your sample slope, whatever you get from your sample, minus beta sub 1, which most of the time is going to be 0. So that's just going to be 0, divided by SE sub B sub 1, which most of the time is going to be given to you, or it's going to be found using the calculator. So this calculation should be really, really easy. Degrees of freedom here. We're dealing with n minus 2 because we're dealing with 2 variables. So no longer n minus 1, specifically n minus 2. And n is the number of data points. P-value. We're using a t-distribution. So we're going to look at the chart in the back of the book. Or we're going to go F5 distribution, F2T on the prism. Make sure you know what your degrees of freedom are. So we'll be using this chart. Depending on what the degrees of freedom are is what we'll be looking at. I think it's easier just to go right to the prism and do distribution T. So we have a conclusion. Use correlation R and the p-value from the summary. So we're going to be using both of these to write our conclusions. As always, if p is small, you reject H sub O. If p is not small, do not reject H sub O. So if you get an R value of 0.48, a p-value this low, and what we would say is if H sub O is true, there is a 0.1% chance that the slope is 0. So we reject. We're saying there's that there is going to be a relationship because there's a small chance that there is no relationship. So we reject that since there's a small chance of it, and we're going to say we have evidence of a relationship. But specifically, I have strong evidence because this p-value is a strong p-value. I have strong evidence that the slope is greater than 0 and that there is a moderate positive relationship. Adjectives are very important here. Strong evidence because p is 0.01. Moderate because r is 0.48. It's a moderate relationship, specifically a moderate positive relationship. I'm going to do one more example for that. Let's just say that R is negative 0.89, and I have a p-value of 0.03, not nearly as strong. So now I'm going to say that I have moderate evidence. The p-value gives me evidence of a strong, 0.89 is pretty strong, negative relationship, which means in terms of parameters, obviously beta sub 1 would be less than 0.